So shortly after a student learns about the definite integral and its connection to the area under a curve, the mean value of a function on an interval is often introduced. Sometimes this is called the average value of the function on the integral. But what about the median value of a function? That seems not to be introduced in typical calculus classes, and that's what we're going to look at today. But before we do that, let's recall the expression that gives us the average value of a function and see maybe why it's the right choice, and see if that can motivate us to make the right choice for the median value of a function. And I learned about the median value of a function in a couple of different places. There is an article from Math Magazine that you can find pretty easily, but all of those expositions follow the same construction, and so I think this is maybe like a well-known concept, or at least like the basic idea is a well-known concept. Okay, so anyway, let's recall that if we have a continuous function on an interval AB, the mean value of f on AB, or the average value of f on AB, is given by the following expression. So we'll call it f average, and it'll be 1 over b minus a times the integral from a to b of f of x dx. And the idea here is that the average value of the function is, well, whatever height you'll need to make a rectangle with the same base, where that rectangle has the same area as the area under the curve. So here's a little bit of a mock-up of what we've got going on here. So the area under the yellow curve is the integral, and the area under the blue, or the area of the blue rectangle, will be the average value times b minus a. And so that's like a graphical expression of what's going on here in this magenta box. Okay, so let's see why this is the correct expression for the average value of a function. And in order to do that, let's maybe recall how to take the average value of some numbers. So let's, like I said, recall that the mean value of the numbers a1 to an is equal to their sum. So a1 plus a2 up to a sub n over n. So we're not doing anything fancy here. And now next we're going to take a familiar step for integration at least, and that is we're going to write the integral as a limit of a Riemann sum. But in order to do that, we need to make a so-called partition of our interval. Okay, so let's do it like this. So we're going to define these numbers x0, x1 up to x sub n as follows. So let's maybe draw our interval. So that's going to be our interval from a to b, and a will be x0, b will be x sub n, and then everything else will be in the middle. So there's x1, there's x2, there's x3, then way over here is x sub n minus 1. And the distance between each of these maybe parts of our subinterval will be fixed. So this is not necessary to create the precise definition of the integral, but it's a typical way to do it in an introductory calculus class. So let's maybe point that out. So this distance right here we'll call delta x, and that's going to be the same thing as this distance right here, as well as this distance right here, and so on and so forth. But notice because of that, we can easily write delta x in terms of the length of the entire interval and, well, the number of pieces we're cutting it up into. So let's notice that delta x is equal to b minus a over n, because we're taking an interval of length b minus a and dividing it up into capital N parts. Now, I would say that it stands to reason that the average value of a function could be defined as follows, or on this interval could be defined as the limit as n goes to infinity of the mean value of, well, that function taken on all of those xi points. So in other words, it's the mean value of f of x sub 1, f of x sub 2, so on and so forth. But notice that we can use the definition of the mean that we well know in order to write this in a kind of nicer way. So this is the same thing as the limit as n goes to infinity of, I'm going to write this as 1 over n and then the sum as n goes from 1 up to capital N of f of x sub lowercase n. Okay, nice. Oh, but look at this. We've got this 1 over n term here. And notice that delta x is simply b minus a over n. So we could maybe exchange some things over here and note that delta x over b minus a is equal to 1 over n. So that means I can write this as 1 over b minus a, and then the limit as capital N goes to infinity of delta x times this sum as n goes from 1 to capital N of f of x sub n. But what did we just gain? Well, we just gained something that is equivalent to the limit definition of the integral, if you will. So we have 1 over b minus a times the integral from a to b of f of x dx. So let's maybe go through what we just did. So the average value of a function, well, I think that could be reasonably defined as the limit of, well, n values of that function as those n values are equally distributed between the endpoints. That especially makes a lot of sense if you have a continuous function. But now using the definition of the mean, that leads very, very quickly to this integral which gives us the average value of a function. Okay, so now let's take this as motivation to see if we can come up with the median of a function. Okay, so let's recall what the median of a finite set is via a couple of examples. So the median of the set A1, A2, A3, A4, A5, A6, A7, where these are in increasing order, is A4. It's the middle term. So notice that there are 3 elements smaller than A4, and there are 3 elements larger than A4. Now, let's also suppose that these are increasing, although I haven't written it down, but now we've got an even number of them, so there's no middle term. Well, generally the rule is to take the median to be the average of the middle 2. So in this case, it would be B3 plus B4 over 2. So the median is like this thing right in the middle. And again, there are 3 values that are smaller and 3 values that are larger. So if we're looking for the median value of a function, perhaps we could do this limit trick that we did for the average value of a function. In other words, we could define f median to be the limit as n goes to infinity of the median of, well, I've written it as an odd number of values just to make it simple so that we've got something, but since n is going to infinity, it doesn't really matter here. So this would be f of x sub 1, f of x sub 2, all the way up to f of x sub 2n minus 1. Now, let's prove this simple claim first before we come up with a nicer formula for the median. And that is if f is a monotone function, in other words, it's increasing or decreasing on the interval a to b, then the median value occurs right in the middle. And so here's a little graph of that situation, but I think this is pretty clear why it should be true. So here we've got an increasing function, and notice this f median here, well, that's the value of f at the thing right in the middle, the average of a and b. And the idea here is that there are b minus a over 2 values of f above and below this median. So the ones above go from the midpoint up to B, and the ones below go from the A up to the midpoint. Okay, so anyway, let's now prove this claim. So let's note the following. So for all, maybe we'll say A, which is equal to x1, which is less than x2, which is less than x3, all the way up to x sub 2n minus 1, which is equal to b, we have the following. We have f of x sub 1 is less than or equal to f of x sub 2, which is less than or equal to f of x sub 3, all the way up to f of x sub 2n minus 1. And that's just because we have an increasing function. Notice this is not strictly increasing, and in fact, sometimes functions like this are called non-decreasing, but we'll use this non-strict increasing thing here. Okay, so now let's assume that these are equally distributed, because that's really the only thing that makes sense for calculating the median over this interval. Okay, so let's do this using the standard parameterization of these. So in other words, x sub little n will be equal to a plus, well, it'll be delta x times n. So delta x will be b minus a over 2n minus 1. So let's write that, b minus a over 2n minus 1 times n. But now I think it's pretty clear that since we've got this ordering right here, the median of the set containing f of x sub 1 up to f of x sub 2n minus 1 is simply equal to f of x sub capital N, because that's the one right in the middle, given our construction with an odd number of subintervals here. Okay, but let's note that that's going to be f of a plus, well, we'll have b minus a over 2n minus 1 times capital N, because that's our index. Maybe let's write this as b minus a times capital N over 2n minus 1. But now let's let n approach infinity, capital N that is, and notice that'll make this approach 1/2. And we're able to bring the limit inside because we've got a continuous function here. Okay, so now let's note that as n goes to infinity, well, like I said, that inside will go to 1/2, but then after simplifying here, we'll get f of a plus b over 2, which is what we claimed for this increasing or decreasing function. Obviously, we just proved it for an increasing function, but all you have to do is maybe mirror this and you have the proof for a decreasing function. There's nothing really going on there. Okay, so now let's move on to a more general continuous function. So we just showed that if we have a monotone function, it's fairly easy to find the median. That being said, if we've got a function that's not monotonic, so it's got increasing places and decreasing places, it's a little bit trickier, and that's because we don't quite have a calculational method of finding the median like we did for finding the mean. But we can kind of hack one together via the following fact, which I won't prove, but you can find a proof of it pretty easily. And it goes like this. So if we set g of t equal to the sum as n goes from 1 to capital N of t minus a sub n, where these numbers a sub 1 through a sub capital N make a set, then the median of that set of the a numbers is equal to something that I'll call lowercase t, where g of t has a minimum at that lowercase t. So maybe we could call this like lowercase t naught. And then we could maybe clear this up by saying that the minimum of g of t equals g of t naught. So at least that gives us like something to work with calculationally speaking in order to get the median of a function. Okay, so anyway, let's get back to our setting. So we've got our interval a to b. We've broken it up into pieces just like we did before. But now we want to build something like the function g. Okay, so how might we do that? Well, I think maybe this is like a nice way of doing it. So g of t could be equal to the limit as n goes to infinity of the sum as lowercase n goes from 1 to capital N of the absolute value of t minus f of x sub n. So that would be like for expressing the median of f of x sub 1, f of x sub 2, all the way up to f of x sub capital N. Oh, but now looking at this, there's a little bit of a problem. And that problem is because we're adding up a bunch of numbers, well, and then we're taking some limit, but those numbers might be quite large. So we need to tame them a little bit. But the way to tame them is to multiply by something. And so let's multiply by delta x just to tame this sum. But now, once we've done that, what have we done? Well, we've built an expression which is an integral. So note that this is the integral from a to b of the absolute value of t minus f of x dx. Great, so that'll be our function g of t in our setup. And that really motivates the following expression for the median of a function. So I'll just say that the median of f of x as x ranges all over all a and b, which we'll maybe call f sub median, is equal to t naught, where the minimum of g occurs at t naught. Okay, cool. So now let's look at graphically what's going on here. So let's get a function on the board. So let's say our function is something like that. And if we want to minimize this function g, well, what's really going on here? Well, let's get an a and b on the board. And here's the lower bound of our interval a, and here's the upper bound of our interval b. So it's something like that. So I think it's not so hard to see that this function g will be calculating the area between the horizontal line at t and the curve f of x as t kind of moves up and down. So if we want to minimize g, then we're looking for the t value that minimizes that area between the curves. So I don't know, maybe just kind of eyeballing it, that would be something like this. So we're minimizing this area. So notice if we were to move it way down here, we would get pretty big area. If we were to move it way up here, we would also get a big area. But that one seems to be at least close to the minimum. And so just to reiterate, our median is not the minimum value of the function, it's where that minimum value occurs. Okay, so let's work out an example. Okay, so for our example, we'll find the median of the function f of x equals x times x minus 2 on the interval from 0 to 4. So I've put a little mock-up of what's going on here. So I've got my function f of x, which is this yellow curve. And then I've got my horizontal line t. And notice that I've shaded in magenta the area between this horizontal line t and our curve. And recall that that area is our function g of t, which we'll write down an equation for in just a second. And the median value will be the t value that minimizes that area. So I think that what we have right now definitely doesn't minimize that area, but at least it gives us an idea of what the picture looks like. Okay, so let's write down an equation for g. So g will be the integral from 0 up to 4 of the absolute value of x squared minus 2x minus t dx. But now what's nice about this is we've got a quadratic function in x, and we can solve that for x to get an intersection point. So we can get like this point right here, or at least the x coordinate of this point right here in terms of t pretty easily. And well, we can do that just by setting the stuff inside of that absolute value equal to 0. So let's do that down here. So we have x squared minus 2x minus t equals 0, but I might as well just write that as equals t. That's going to be where those two intersect. But we're looking for the positive intersection point. We'll keep that in mind. So I might as well complete the square on the left-hand side by adding 1 to both sides. And then I can factor. This is x minus 1 squared equals t plus 1. Taking the square root, we'll get x equals 1 plus the square root of t plus 1. Of course, like I chose the positive root there because it's kind of clear that our intersection happens in the positive root. So notice between 0 and this x value, which maybe let's go ahead and point out this x value is 1 plus the square root of t plus 1. The line is on the top. And from this x value up to 4, the curve is on the top. So that means I can easily write this as the integral from 0 to 1 plus square root of t plus 1 of, let's see, t minus x squared plus 2x dx, because the line is larger. And then plus the integral from 1 plus the square root of t plus 1 up to 4 of x squared minus 2x minus t dt. Now, doing this calculation is not super involved or anything, but we won't skip it here because it's not super interesting either. But what you end up with in the end is 20 over 3 minus 2 times t, and then plus 4/3, and then 1 plus t to the 3/2. Great, and then let's just bring down our g of t. So this is our g of t function. And recall the median will be the t value where the minimum of this function occurs. So where do minimum values occur? Well, they occur where the derivative is 0. Well, I guess the second derivative has to be positive as well, but we won't check that part. We'll just find that where the derivative is 0. Okay, so taking the derivative of this will give us minus 2 plus, let's see, that'll be 2 times 1 plus t to the 1/2. Like I said, we need to set that equal to 0. And then let's get to solving for t. So moving some things around, I think it's pretty clear that we get 1 plus t to the 1/2 equals 1, which that carries down to t equals 0. And so there we have it. This will be the median value of our function. So I'll write it down here. F median equals 0. And where does that occur? Well, let's notice that occurs at x equals 2. Oh, but x equals 2 is right in the middle of 0 and 4 again. So in fact, what happened here is we happened upon another special case. And let's notice if we look at this value at x equals 2, half of the values of the function are smaller. Notice all of the values between 0 and 2, and half of the values are larger. All of the values between 2 and 4. And in fact, something like this will happen if you do this with any sort of quadratic function. And it's actually the fact that a lot of times when you're calculating this median value of a function, you use some sort of symmetry or it falls into one of these classes. And that's because if you take a more arbitrary function, even something like a cubic, you immediately get like an integral, which is calculationally very difficult. So if you're still around, thanks for sticking around. And if you haven't subscribed yet, maybe consider subscribing. It would really help out the channel. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.